Hello, everyone. I'm Andrew, and Vikas is sitting there, but will come up soon. So a little recap. I'm sure people all know what TinyML is, but basically there's a whole bunch of interesting applications, including the person detection, keyword spotting, and anomaly prediction. And so kind of when trying to get these applications to run on small, low-power devices, you're doing stuff to eke out as much performance as possible. So you're trying to maximize the use of your memory, your processing cores, whatever you have, with the goals of decreasing latency, all while kind of trying to balance this energy consumption issue. So what we're trying to do with MEMA, which is the minimizing external memory accesses, our goal is to have a framework such that you can be deploying stuff to these microcontrollers and working on minimizing your external memory accesses. And we choose to focus on this because this tends to be one of the bigger limitations on these systems. So what we do with MEMA is we consider the local memory size as well as kind of the bandwidths available between the caches. So depending on the system, you may have one layer of memory or multiple layers of memory. And what we do then, once you have all the information about the system, is we can analytically derive a schedule that will minimize memory accesses. So in this paper, we focused on matrix multiplication, but other similar nested loop things, direct convolution, et cetera, would work well. So the diagram there just kind of shows that we first analyze the hardware, then we pick a kernel, and then we can do runtime scheduling and then deploy it on the hardware. So kind of to put things in context, a lot of systems can be categorized by this roofline model. So in this diagram, we show a few ARM controllers, so the microcontrollers up to Raspberry Pis. And so depending on what your algorithm is, you're going to be somewhere underneath each of these rooflines. And in the case, the regions where the roofline's kind of slanted, that means the problem is memory bound, and the flat parts, it becomes compute bound. And so what you want to do is you want to move as their arithmetic intensity is up as much as possible to move things to the right. And as you do that, basically, when you're memory bound and you move to the right, you're able to increase your throughput. But when you're compute bound and you move it to the right, you're decreasing the memory accesses, and that would have an effect on the amount of power you use because you are then doing less data accesses, which increases power. So kind of how we do it is we identify the system characteristics, and then with that we can figure out possible tile sizes. So depending on how many processing cores you have, specific tile shapes are possible, others are not. So we kind of figure out which are available and pick what's the best for that specific system. And then once you have the tile size, you can compute how much I/O you need for each tile calculation. So depending on the order that you move through those tiles, you're going to have different data accesses. And so if you enumerate that, you can then pick one that minimizes data accesses. And so yeah, this method can apply to more than just matrix multiplication, but I'm going to give an example of matrix multiplication here. So basically we illustrate what we do with these diagrams. So on the left is your standard tile matrix multiplication. So you have, you tile it, and then you have a bunch of these smaller vector operations. So you're doing vector outer products. We focus on outer products just because it allows us to have more partial data, which I'll show in B and C. So in the diagram B, what you can see is that you have data kept locally. So you keep the piece of that C tile stationary, and then you stream in your operands. So that way you're not reading and writing your partial results a bunch of times. So you only ever bring it in once and write it once. But you have a cost of streaming A and B. The other case is shown in C, which is where you keep one of the operands stationary. So that's showing an example where you keep the B tiles stationary. This is kind of similar to Godot's algorithm, which is a common method for CPUs. So instead you're keeping that stationary, but now you're going to have to read and write the results a lot more. But there's certain cases where that's actually beneficial. If, for example, the B matrix is significantly bigger than the C matrix, then you don't want to do that. So with matrix multiplication and most of these things, the loop order doesn't matter. So this is an example of just a tiled matrix multiplication. And what you can do is you can permute the loops as much as you want because the result will still be correct, which is kind of what our stuff hinges on, is that we can move the loops around to pick the one that minimizes data accesses. Then that's because certain dimensions will have more data reuse opportunity. So for example, if the M dimension is really big, then you're going to have a bigger, you're going to have an opportunity to reuse a piece of data along the M dimensions M times, which is going to be much bigger than say N or K. In this case, these graphs are a little small, but basically the top two are showing all we do is we switch the order of the M and K loop, and depending on the skewness of the matrix, that results in better throughput. And so we make that decision using what we call the MEMA equations. And so what you can do is you can calculate the I/O, which is going to be based off the tile size as well as the loop order. And using that, right, there's kind of, we're assuming that only one piece is kept stationary. You can do some corner turning stuff to add another level of reuse, but in general, we found that's not really worth doing because it only adds like 1 or 2% for a significant amount of overhead. So we're just looking at keeping the operand A stationary, operand B stationary, or the result tile C stationary, and that corresponds to N first, M first, and K first. So once you pick your tile size, you can plug this in and just pick the smallest loop order. Yeah, I believe I will turn it over to Vikas for the evaluation. There you go.
Thanks, Andrew. So I'll just talk about some of the evaluations we did to compare our work to some of the state-of-the-art. So we worked on 3 platforms, because you saw 3 roof lines before, and those platforms are the Arduino Nano, then the STM, that long name there for that hardware, and then the Raspberry Pi 4 Model B. And basically they're ordered in terms of like hardware complexity. So the Arduino Nano is the simplest one, and the STM, the Raspberry Pi 4, has like 4 cores, plenty of DRAM bandwidth, but it's still relatively like small relative to a like Intel CPU. And then the performance metrics for evaluation, we really just care about the computation throughput, the number of memory accesses, so not memory size, but memory accesses, and then the energy consumption in millijoules. And then to measure all of these metrics, computation throughput is pretty simple, but for energy, we use this power monitor in the lower right-hand corner. It's a Monsoon Solutions power monitor, and we just measure the USB power for the Arduino or the Raspberry Pi or any of these devices. So the workloads we evaluated were the TinyML perf benchmark and the deep learning matrix collection, DLMC. So that includes a bunch of transformer models and all of their matrix shapes and sizes. And we just compare, we run MEMA on these 2 benchmarks and then compare them to the existing libraries of ARMPL. So ARMPL and ARM-CL, those are both on the Raspberry Pi. And then CMSIS-NN is on the STM and Arduino hardware. So we'll talk about DRAM I/O first. So this is on the Cortex, the Raspberry Pi hardware. So we see here that MEMA, in terms of performance, in terms of throughput, it either matches or outperforms the state-of-the-art competitors, ARMPL and ARM-CL. And if you look at the DRAM bandwidth, it also utilizes like much less DRAM I/O in this case, not bandwidth. We actually counted the memory accesses. So bandwidth or I/O, either way, it minimizes the DRAM I/O using this like scheduling technique that Andrew was talking about and all of those equations. Those equations are basically embedded into like our code and allows us to choose the correct kernel depending on the matrix shape. So like on the bottom axis, the x-axis, you can see all these different matrix shapes. These are the transformer model matrices, assuming a sequence length of 2048. And as you can see, the skews are all kind of different. And on the right diagram, the throughput diagram, our throughput is either like, the same or better than anyone else, and it also has less variance. It's kind of similar because we're doing this kind of optimal scheduling, picking the right loop order whenever we want to. So now I'll move on to the smaller hardware, the Cortex-M4 Arduino Nano. The STM-M7 results are almost identical, so we omit them from here. But again, you can see that the MEMA kernels are achieving a higher throughput, for a much higher throughput for FP32, but for a fixed point, so they achieve a higher throughput, but it's not quite higher. And another interesting point is, if you look at the throughput for floating point and the integer operations, it's about the same in terms of operations per second. You see it's like 25 megaflops versus 25 mega integer operations for the Q15 operations. And the reason for that is that the data on these devices, even if you're using like int8 or int16, they're always packed into 32-bit words. So you eat a huge cost in unpacking them. And the unpacking is kind of like, you would expect to get like 2x throughput compared to the floating point, but you don't, because like everyone suffers from this. So CMSIS and us, we all have to unpack our data, and that unpacking just eats up a bunch of cycles. But regardless of that, even though you have to unpack, we're showing basically that with the scheduling, like you can still squeeze out a little bit more performance than the state-of-the-art competitors. And not only can you squeeze more performance, but you can do this with less energy. So for the floating point case, it's clear that like the outer product is like outperforming the CMSIS inner product based computation. But then if you look at the energy usage for the Q15 multiplication, we're also using like significantly less energy in like the first like couple layers, or the first couple data points here. Those are like very like heavy duty layers. And this is because of the scheduling. So even though we have this like unpacking of the data problem, we can still get energy benefits through scheduling. Yeah, so in conclusion, this MEMA framework is able to improve throughput, reduce energy consumption, reduce the amount of DRM IO that you do, and hopefully they enable new applications and like longer battery life and all that. But again, you have this Jevons paradox that we talked about in the beginning of the day, and so we don't have to add new silicon at least, so we're sustainable in that way. But we might suffer from the Jevons problem. But anyway, like future work, hopefully, we're looking at integrating our methods into existing libraries like TVM or the polyhedral compilers, and also looking at like extending our methods towards sparse matrices and even more operations like, for example, depth-wise. Even though they're very similar, it'd be like a nice engineering and like interesting experiment to see if we could do this like fully integrated end to end. But anyway, that's our talk, and thank you.